Hello everyone, my name is Liam Sponigal and welcome to my final reflection presentation for ME 341 Experimental Methods in Mechanical Engineering from Fall 2025. Over this semester, I've worked through 6 major experiments in a group of 5 students. The experiments were of varying topics that encompass the teachings of many different courses I have taken throughout my college career. Each lab helped me further hone my skills in instrumentation, data acquisition, analysis, and technical communication. Today, I'll reflect on what I've learned, how I learned it, and how these experiences will help shape my career. This course challenged me to connect theory with practice. Each lab required not only careful experimentation, but also structured technical writing and in-depth knowledge on a wide range of engineering topics. I learned how to better design experiments, collect reliable data, and communicate findings clearly. Writing reports taught me precision and organization. Oral communication in this reflection has helped me practice presenting technical ideas, and working with the same group helped me build strong relationships and further develop my communication skills. Engineering ethics also played a key role in this course, ensuring accurate reporting and responsible handling of data. Across the 6 experiments, I explored a diverse assortment of technical subjects. Lab 1 covered calibrating pressure transducers, which taught me about hysteresis, linearity, and uncertainty analysis. Lab 2 examined strain gauges, showed how bridge circuits amplify sensitivity, and how error propagation quantifies confidence. Lab 3 revolved around vibration testing. My group and I were able to experimentally demonstrate resonance, damping, and the importance of boundary conditions. Lab 4 focused on signal filtering and compared analog RC circuits with digital moving averages, highlighting trade-offs in noise reduction. Lab 5 involved transient analysis of RC and LRC circuits, which connect the theory of time constants and natural frequency to real attainable data. Finally, Lab 6 investigated DC motor characterization. This tied electrical input to mechanical output, validated back EMF theory and efficiency trends. In all, each experiment reinforced the link between the theoretical models and real-world behavior. Throughout this course, I became proficient with a wide range of laboratory instruments: oscilloscopes for time domain signals, strain indicators for microstrain testing, deadweight testers for pressure transducer calibration, and function generators for electrical excitation. This slide outlines all of the different instruments that I used during the execution of the 6 experiments for this course. From this, it can be seen that the most versatile, widely used, and vital laboratory instruments in relation to these experiments are the oscilloscope, digital multimeter, and function generator, as they were used in at least half of the experiments this semester. Learning to configure these tools correctly was critical, from zeroing strain gauges to ensuring a floating piston in the deadweight tester. These experiences improved my confidence in laboratory instrumentation. Here's a closer look at 5 of the experimental setups used in this course. This should give you a better sense of how the instrumentation is implemented and of the laboratory conditions when conducting these experiments. Writing 6 technical lab reports definitely strengthened my ability to effectively communicate complex experimental results. I am now practiced with creating APA citations, well-structured report formatting, and clear explanations of data and uncertainty. In order for proper completion of these reports, teamwork was essential. Each member contributed to different sections, and I often focused on the discussion and interpretation. As a group, I feel that our communication skills improved significantly throughout this course. A great example of this came from Lab 2. The due date was improperly put onto Blackboard for a day earlier than it was supposed to. 2 of our group members did not notice this, and the other 2 were very stressed that they had not completed their portion of the report by the night Blackboard said it was due. Initially, our communication about this was ineffective and emotionally fueled, as 2 members felt that the others were not doing their share and the others felt that they were being harassed. However, after the next lab, we all got together and talked through the situation. We were able to establish an even distribution of work and create a plan for the lab reports going forward. After this, our lab group was much more effective at communicating and completing our assignments in a timely manner. This collaboration mirrored professional engineering projects where clear documentation and shared responsibility are vital. And this experience will absolutely help me know how to better collaborate going forward. Data acquisition and processing were a central part to every lab in this course. Using WinDAC, oscilloscopes, and Excel, I learned how to process raw signals into meaningful results. Regression analysis helped me validate theoretical models, while uncertainty propagation quantified confidence. For example, in Lab 2, error propagation showed how micrometer uncertainty dominated strain calculations. These skills will be directly applicable to engineering analysis and will help me to be a more effective experimenter in the future. Each experiment connected classroom theory to practical engineering. Pressure calibration emphasized sensor reliability. Strain gauges linked material mechanics to measurement. Vibrations and transients tied system dynamics to control applications. Filtering showed how engineers manage noise in their signals. DC motor testing bridged electrical and mechanical domains. While these experiments were small scale, the principles learned from conducting them is applicable at any level. For example, the testing from our lab on vibrations and transients is similar to how a car manufacturer would assess a suspension system, particularly one using leaf springs, or how a structural engineering firm would design a damping system for a building in an area with a lot of seismic activity. These applications demonstrated how experimental methods underpin design, validation, and troubleshooting in engineering practice. Engineering ethics and experimentation dictates that you must report data honestly, acknowledge uncertainty, and avoid bias. For example, in Lab 1, calibration errors could mislead if not documented. Instead of doctoring the data to make it fit with the theoretical model, we acknowledged that there was clearly error in our data and examined what the source of it could be. Additionally, in Lab 6, efficiency calculations required transparency about assumptions. Without this, any insight gleaned from the experiment would be practically useless. This course reinforced that engineers must uphold integrity in both data collection and communication. My most interesting discoveries from the experiments were seeing resonance visually in the vibration lab with the use of the stroboscope. The beam's dramatic response at natural frequency was very interesting to see firsthand. Also, observing how digital filters smooth signals but introduce lag, which is an important trade-off to be aware of in system design. Lastly, discovering that motor efficiency increases with speed, validating theoretical expectations. These moments made abstract concepts tangible and memorable. Additionally, important takeaways to reiterate are the importance of communication between group members, how to effectively and ethically report experimental findings, and the numerous opportunities for error in experimental data collection. Through this course, I have gained several skills that will be essential in my career, including effective instrumentation and measurement for testing prototypes or systems, data analysis and uncertainty evaluation for validating designs, technical writing and oral communication for reporting results, and lastly, teamwork and collaboration for project success. These are transferable skills that all mechanical engineers must use daily in industry and research. In conclusion, this course has taught me how to design experiments, use many different laboratory instruments, analyze data, and communicate results with integrity. Creating this presentation has also helped me reflect critically on my learning throughout the course. If I had unlimited time, I would improve my presentation by adding more animations, an interactive concept map, and more real-world examples to connect the labs to industry applications. Thank you for listening.